has a generator on their farm. Great. Have you got anything to add at any of these points for the edification of the class? Let's discuss it. I think we've got enough gap and enough space to be able to do that. So we'll start with a picture of what an irrigation, typical irrigation type genset is. I will point out a handful of things, and there's a lot of variations, but you typically will have a natural gas motor. Okay. For the most part, the most effective ones, the ones with the most application have been industrial style motors, ones that are going to increase the lifespan and have higher reliability, as well as more sophisticated regulators than the automotive style. You can still do it on automotive style, but we're going to concentrate mostly on the industrial style. This particular one, if you notice, it has cooling coils. That's an option that we'll discuss at some point. Just the way it's equipped, it's just like a natural gas motor that's going to power a gearhead. Instead of powering a gearhead, you're powering a genset off the back that's creating three-phase electricity. That's also what we're going to talk about. You can generate one phase, you can generate high volt, low volt, but we're going to talk about 480 volt, three-phase generators with power being generated off of natural gas gensets. Other things you'll look at in this picture, this is close to a well. Obviously it has to be if you've got cooling coils. This is a single well on here with controls back here. And then in this particular application, there are also off-site wells that the electrical lines run to, and then you can see there's additional motor controls back here for each one of those well sites. So scenarios where you will want to consider a natural gas genset. It's not for every application, mind you. If you've got electricity there that's reliable, you're probably not going to look at this scenario. If you've got, well, we'll just go through these steps and there'll be a handful of scenarios. But usually you've got limited capacity of the existing electricity infrastructure, meaning one, you don't have power delivered yet, or two, you don't have the feasibility to have power delivered. Some of these outreaches, the cooperatives or the provider, don't have enough capacity on their grid to bring you power. This would be a great first scenario for you to look at that. Next one, if you currently have natural gas infrastructure, and this is pretty ubiquitous across this area, you're going to have gas lines, gas being the, do we need a correction on that? Okay, gas being the most common and affordable fuel for irrigation in this area for a long time. That's a fortunate privilege for this, is you can build off of that infrastructure. Also, if you're looking for declining water scenarios where you've had reduced power requirements, reduced water at multiple wells, we're no longer having full power, half or less than half loaded natural gas motors, and you want to look at a smaller electrical motor or a submersible, like what was mentioned earlier, your efficiency really works when you're peaking towards the load of your natural gas motor or your diesel motor, whatever your internal combustion motor is. As you get closer to that 100% mark, your efficiency is where you're capped at. So if you're operating at a lower loading, really the mathematics of it is your internal losses from heat, your thermal losses from turning that much steel, you're going to be turning that whether you're loaded or not. And so your efficiency of what power you're producing goes down. And so with some of these cases where you go from 500 gallons per minute to 250 gallons per minute per se, and you want to look at a smaller pumping plant, this is another criteria that helps make this decision for converting to gensets. And the other, if you're looking at a potential for lower energy costs, if you're on the margin that way, in most every case that I've seen natural gas gensets for a long period, for about 10 years now, going back to the fall from the peak of $12 gas, basically when gas came back to normal costs, ever since then natural gas generation of electricity has been cheaper than grid power. And we'll go through those numbers. One thing I will mention is if you are going to consider natural gas gensets, you're going to become a utility company on multiple fronts. Because now you're not just dealing with your water, you're also dealing with your natural gas that's coming in, you're dealing with your production system to generate electricity, and now you've got to become an electrician. You're dealing with power lines, which are delivery power lines, in addition to your starters, controls, etc. So you have to be pretty well-rounded and pretty competent in order to operate this system. And keep in mind, it is very comprehensive. At this point, you're dealing water, power, and natural gas all in one. Above and beyond, you're managing your crop. So here's some costs to look at. This is comparisons just so we're on the same page in terms of how we're figuring these costs. So we look at BTUs per unit, so that's British thermal units or the measure of potential energy within this fuel or power source. Okay, so in natural gas, we're looking at 1 million BTUs per MCF of fuel. Gasoline, we're looking at 125,000 BTUs per gallon. Diesel, 139,000 per gallon. Propane, 91,000 per gallon. And electricity per kilowatt hour, we're looking at basically 3,400. Again, when we go through cost per unit, you can see those. These are moderately current costs. And then if you translate these through, you can look at dollars per million BTU. And you can see that natural gas is so much cheaper than the rest because it's in excess right now. And so you end up with this $3 gas. And that difference is really where this dynamic of being able to generate your own electricity comes in. Okay? And we'll talk about efficiencies as well, because this is the other factor. We take these costs per unit, look at the efficiency on site, look at natural gas, an average of 21%. These industrial motors, I will say, to back up Leon's slides in testing, if you're using a modern cat or a rebuilt cat, you're going to be in that 23 to 25% almost all day long. If it's firing right and the timing's good, you're looking at 23 to 25%.
Even depending on loading?
If you're loaded properly, yes. I mean, you're going to lose a little bit, but let's talk loaded properly, okay? Yeah, if you've got, you'll laugh at this next picture. Okay, so bear with me, but yes, this is presuming you're loaded properly. I will say, however, that on these natural gases, I've tested many automotive style that are 15% efficient. Okay, and that's just robbing you blind on your fuel costs. Electricity, this is a combined comparison, 88%. This is just for an average. You've got a modern Prima or a premium NEMA. They're going to call it inverter duty motor at the moment. That number is going to be much higher, something like 95%. If you're buying a new electrical motor, a vertical hollow shaft motor, you're going to have to buy an inverter duty premium motor. It's not available any other way. That change happened about 18 months to 2 years ago. And there was enough of a backstock that guys are trying to get the cheaper motor. It's just not an option anymore. So if you're looking at a vertical hollow shaft motor, you're going to look at something that's going to have much higher efficiency. And you'll see how that plays in. That's a big benefit to you. Diesel, 35% engine efficiency. Propane, gasoline, basically the same as natural gas, okay? It can take that range. And then we look at cost per acre inch of water. If you go through these numbers and do this cost of fuel on a 400-foot pumping depth at 20 psi, you can see that you're going to be pumping cheapest with natural gas, then next with electricity, where electricity really turns the tables, being one of the more expensive at the bottom. It jumps right up to the top to be comparable for natural gas, obviously just because of the efficiency. Okay, so those are the two factors we're looking at. Cost of the bulk unit multiplied through the efficiency potential of the systems. So this is the picture I'm talking about. This is a nice looking a cat motor on a Genset site that I was test pumping. This well, and you guys want to be concerned about your water, this well is drilled 1,900 feet deep, pumping from 850 feet. Okay, so when we start to gripe about big motors and horsepower, there's a reason why there's this big of a diesel tank through here and had to be filled multiple times during this test pumping. Okay, we don't use diesel primarily because of that and because these motors are ridiculous. Gas prices, previous 12 months, we look at it. The peak was at $3. For the sake of what we're going to work through in this discussion, we'll use $3 fuel. But I think you'll know your costs can ebb and flow a little bit, depending on who your provider is to. You may have some service charges in there. And then here would be a typical electrical bill. We're doing here, this is off of the center actually. This is a recent one from this last summer. What I did here was combined basically all of these costs and divided the total cost by the energy charge or the energy consumption of about 45,000 kilowatt hours. This is an important point I want to make to you, okay? Because you're going to look at these numbers and you're going to say, oh, my energy is this cost, or my energy is this cost minus my credit. When you're making this comparison, you have to go all the way across all of your demand charges, all of your startup charges, your service charges, etc., because those will be off the board if you're generating your own power. You no longer have those fees. Okay, so when I look at this culminated cost, what I come up with, and we'll use this number throughout, is an average electricity rate of 6.3 cents per kilowatt hour. And I will say across the board, this is a pretty good price. Okay, this is a good rate. I know you want it better, you always want it better. There's some farms I look at that are paying 10.5 cents per kilowatt hour, and there's some that are smaller loading in more isolated areas that are 12.5 cents per kilowatt hour. Okay, this is a good number. This really lends to why we want to be talking on this Genset about what the comparison is, because you can see that you can even improve that number if the scenario is right on the natural gas prices. So this was the test we did in this area, is in Sunray. It's getting on 8 years ago now that we did this. Okay, this was one of the first Gensets that we tested, so I went out and measured the fuel, measured the loading, measured the electrical at each site, measured line losses, etc. And this is our summary. This was part of a REAP project at the time. It was one of two that I did on this particular farm, and was able to, and really in this process, convince myself that generating electricity on site with natural gas is a very good option if you've got the wherewithal to do it. This particular farmer had the wherewithal. It was a great option. They got a lot of government funding to help them as well because of the mitigated costs of generating power on site versus their older natural gas equipment, which was in need of replacement anyway. So if you follow me through here, we look at this $3 per natural gas cost. At the time it was $4.50, and it still made sense to do this. We measured the fuel coming in. So basically stopwatch and this was a Roots style gear driven gas meter. We measured 10 cubic feet in 26 seconds, and 20 cubic feet, 51.03 seconds. When you average it out, it was using just shy of 1,400 cubic feet per hour at a cost per hour of $4.19. Okay, so that's his fuel cost per hour to run this Genset with the particular loading that we have. Okay, so that's the input side that we're looking at. And you compare that to the output side, or the generation side. Okay, so the generator output at a power factor that was measured 0.95, and then the legs of the electricity that was generated off of that, and we were generating at just shy of 490 volts and generating 124 amps. When you go through the math of it, you end up with kilowatts, which is the same as kilowatt hours per hour, that we were generating at just under 100 kilowatts, total horsepower of 133. And what we come up with is a cost per kilowatt hour at this rate of 4.2 cents. Okay? So this would be the comparison of what we're looking at now. Remember, the electricity you're buying at about 6 and change, you're able to generate it at 4 and change. Okay, so you're making your electricity for quite a bit less than what you could buy it off the grid from at this particular time, given this scenario. Here's a number to take note of if you're wanting to do some very quick mathematics for yourself. If you take your natural gas cost, dollars per MCF, and multiply it times 0.015, you're going to come up with an approximate number of what it's going to cost you to generate your power. Okay, I think this is probably a good take-home number for everybody that's got this in their mind. I'm not usually a guy that's big on rule of thumbs and slide rules and type stuff, but this number does hold up. Okay, so that's a number you can look at. So let's look at some installation costs, the hardware cost, the capital portion. If we look at a 3-phase power line coming in with transformers, with run, with everything, you're looking at about $10 per foot. This is going to be give or take. In some cases it may be more expensive, in some places a little less. And you're looking at about $10,000 per 3-phase drop. And I'm estimating this off of a 200 amp service coming in, which is going to basically be the size you're looking at. If we take that same loading, the 150 kilowatt natural gas Genset, new, you're looking at $65,000, a reman, you're looking at $55,000. And that's going to be a complete unit on a skid. These particular prices include a radiator and a fan and all of that. Okay? The reason I put these up here because they're so close is that if you are looking at bringing new power in, if you have to run line a mile, it's basically going to be a wash in your cost of that capital expense. Setting up the Genset versus bringing in the power line is going to be a wash. And then you can start to compare it on the unit and the margin. We good to this point? Any thoughts, questions?
What's the life on that unit?
Okay, so this unit is in the 10-year range. When you count out the hours of what we irrigate, you should be able to run it for 10 years, and then you would need a major overhaul. And in some cases, you can get the major overhaul, which is in the range of $30,000, you're back going again. Okay, minor overhaul, we'll go through some of those prices later. You're looking at a 10,000 hour operation of minor overhaul. 5 to 7 to 10 depending on your unit. Okay, so genset sizing. Here's a couple of numbers and some considerations to have. Every one of these scenarios is unique. You have to look at the summation of all of your loads that you want to put on this genset. So if you're thinking of 4 wells, you need to know what your loading is on all 4 of those wells. If you're looking at running wire to those wells, you need to look at your line loss across that wire. If you're looking at running pivots off that, you've got to add the pivots onto that. All of those accumulate to how much power you have to generate. And in some cases, you're going to run into a limit. You may need to have multiple generators if you've got a big enough system that you're trying to operate on. The basic number that we'll look at is that 1 kilowatt equals 1.34 horsepower. So for example, if you've got a 150 kilowatt generator, you basically could be in the range of 200 horsepower for what you can operate off that. So keep it in mind, if you've got a couple of 40 horse subs, you do the math pretty quickly. You're going to look at 5 40 horse subs on this, then you have to get really cautious about the math, because what's my line sizing look like? What's my wire down the hole look like? Am I really loading 40 horses, or am I loading 42 horses, or am I down to 33 horses on my sub? Okay, so that all comes into play when you're looking at generating this power. Another thing you want to pay attention to is apparent power. Your modern gensets are going to have really close to unity power. What that means is that there's a phase difference between where your volts are at and where your amps are at. Okay, if they're slightly out of phase, you lose a little bit of power, and that's referred to as the power factor. That's really important in these scenarios because you're going to use inductive motors on these well pumps. What that means is that by default they have a lagging power, which means the volts usually is a little bit before the amps. And you're going to reflect that in the number of power factor. Okay, and that's something that can be measured but must be accounted for. Okay, you never get an improvement in power factor. It's always going to be a deduction. Okay, so you've got a motor that's loaded at exactly 40 horsepower, you're going to need to provide more than 40 horsepower to overcome whatever that power factor loss is. And I'll show you some nameplates where you can see where to find power factor on there, because it's very important in this sizing.
What are the power companies generally give you insofar as that power factor?
So my range of what I actually measured on there, ranged from as low as 75, so 0.75, which is if you can imagine, you can't hardly close a contactor on that. You know, you'll see buzzing in the box at that point. But that's the lowest I have measured, all the way up to high 80s. Okay. The way power factor works is all of the loads that are on the system, if they're all inductive loads, they all contribute back to that line. So you're dealing with everybody's motor that's on that system. So it's going to be much lower than what you can do at your generator.
They're trying to correct that with the capacitors, right?
You can do that locally with a capacitor, yes, but that's expensive, of course, and it's again, never perfect. But yes, there's correction methods.
Go through it one more time and explain the power factor relation to amps to volts.
Okay, so if you think of this as alternating current, okay, the way it works is it's got a sine wave. Okay, it goes up and then down and then up and down. And if you look at that, it does that 60 times per second. That's the 60 hertz. Okay, so it's going to go up and down and back to the middle 60 times per second. If your volts are doing that, what the power factor indicates is how much off phase your amps are doing that. Okay, so you can think of it a little bit like this. Okay, to get the best power, you want the amps and the volts to be hitting at the exact same time. And if they're off one way or the other, it's that's what creates your power factor. And keep in mind, we're doing induction loading, so you're almost always, unless you've got something else contributing, you're always going to be in the lagging position, which means your volts are going to lead, then your amps are going to be behind it. Okay? Thanks for asking. Question in the back?
You may be going to get into this, but one thing I'm wondering about power interruption, the difference between regular service, what you have with this, and then lightning risk, if with the genset you're all underground versus overhead.
Well, so the question is power interruption, and I would say that that's one of the primary reasons to consider a genset in the first place. When you're on grid power, you are subject to brownouts, you're subject to lightning strikes. across a very large area, may not even be in your service area. In terms of on-site risks, your lightning exposure is very similar with a genset as it is going to be with power. You've still got services that are above ground, but you're not going to have transformers that are above ground. So it's similar on site. Your pivot can still be struck. There's still plenty of things that lightning can get you, but you're not dealing with everybody else's equipment potentially being a target for lightning. And you're certainly not dealing with the grid's blackout or brownouts. And I'm glad you asked because I wasn't going to get into that. So let's keep having the questions because I think we've got enough gap to talk through some of those questions. But some other points on sizing that I want to mention is you must be oversized on your generator. There will be D rates based on conditions, namely heat. Okay, some of the gensets that I've used, I'll show a picture later, I've had to get into a 75% D rate because of the tests that I do in Arizona and the heat. It's horrible. It'll just knock the power right down because the heat affects not only the motor now because you've got less thermal efficiency because you're pumping hot air through the motor, but you also have electrical lines, electrical motors that have to transmit and deal with that heat and dissipate it. So you're looking at a D rate, so you need to oversize a little bit. The other thing is continuous duty. You want to make sure that you are setting these up where they're not all the way at their max load, that they're at their continuous duty load. And that's something that you'll find in an industrial motor compared to, say, an automotive style motor. Oftentimes the automotive style motor, we're really pushing our luck when we're running 454s, 350s, and 496s because you're running way past what its continuous duty cycle should be at high RPMs. You get into these lower RPM cat type motors, their horsepower rating is based on a continuous duty rating.
What about starting and your amperage for starting has got to be more, so you got to oversize a little bit for starting.
We're going to get right into that, absolutely. That's a very important aspect of this. I don't know if it's the next slide, but it's really simple. Okay, so now let's talk about maintenance schedule and costs. Steve, here's your slide. Top end overhaul, again, industrial motor, looking at 5 to 7 years at a cost of $4,000 to $5,000. Major overhaul, looking at 10 years plus, depending on how you run it, just shy of $30,000. Your oil change interval on these motors about 750 hours on it, so roughly monthly, and you're looking at 12 to 20 gallons, depending on if you got a 4-cylinder, 6-cylinder, or whatever. Okay, so you start to add that into your maintenance costs. One thing that I would note on this maintenance cost and schedule that's hard to quantify when you're going from multiple natural gas motors down to one natural gas genset and multiple electrical motors is you'll find that there's tremendous savings in going from site to site to site, changing oil on 4 or 5 motors versus one. The same with keeping up with the oil, keeping up with spark plugs, keeping up with tune-ups. When I did the math and the timing on this experiment, it was 8 years ago when I first had done it, I was shocked with how much maintenance came out of that schedule. And in operation, it proved out. That's one of the reasons why the folks that I'd done this study with really developed much more gensets, is it was really economical for them, but it also fit their system very well. Okay, they found that they could get by with managing one natural gas motor without much concern, where they felt like they were running around to 4 or 5 on this almost constantly. So you have to figure out what your pickup's worth, what your time is worth. In my mind, I would say, as somebody who's watched a lot of people manage, you underestimate what your time is worth. If any of you are making crop decisions, your time is not all that valuable, in my opinion, changing oil. You can impact your operation so much more with making the valid management decision on your crop. I know that's a hard thing to do because you're thinking, I'm going to be this, I'm going to be this, I'm the farmer, I'm taking care of all this business. The guys who seem to do the best with it understand that I'm going to take care of this as a means to help me be a very good farmer to be in the field. Some genset outputs, and this is one that we derated usually the 85 to 75%. What I mean by that is we're taking 15 to 25% off the top of that when we're testing wells. Here would be what the outputs on this would look like on the electrical side. This is pretty nice in that it's digital. You also have a similar screen for the motor, so you can look at fuel consumption, etc. Again, this is diesel. It's a little different application, but quite similar. So you're generating 481 volts. In this case, it was loaded at 212 amps. The hertz are right on at 60 hertz. And then this is the power factor here. So this one in this particular case is an old 400 horse motor that's currently being driven through a drive off of this. And so it's got a little bit of feedback, and so you're at 0.93 on the power factor in the lagging position.
And then producing 164 kilowatts.
Yeah, that's what this is producing, 164 kilowatts. Then you'd have a similar readout, and this is the analog style. Again, you're looking at volts, hertz, and your amps. Okay, a couple of points I want to make about this. On your volts, you are always going to be ahead to overvolt versus undervolt. Okay, volts and amps have a relationship, and as your volts go up, your amps can come down a little bit. What that means is you can carry more power through the line with less loss, and you can fully engage your motors. So on these, most of these motors are rated at 460 volts. Most power will be delivered ideally in that 480 range. And if you can generate at 480 to 490 at that gen site, you're going to be much better. And in some cases, you probably are going to need to go look at your pivot, because this is where it gets really interesting when you're generating power. If you don't have, so think of it this way, if you've got all your line going to your pivot, and you've got line loss then going down your pivot, where do you typically burn out your motors first? At the end. Most of those cases are from a low volt scenario. Okay. So you can think of all of these satellite wells really similar to the last gear drive motor on a pivot. The farthest ones out are going to get the lowest volts. You want to generate high enough volts to account for all of the line losses, so when it gets to that particular load, it's going to have all of the volts that you can give it. Most of these will run reliably at 500 volts. If you get to 505 to 510, that's when you start to see tripping issues, you start to see overheat type issues, because a lot of the motor controls will not like that. Okay, so here's some nameplates. This is a nameplate off of this particular generator. So we're talking apples to apples here. First things first, what you're looking at is the ratings. So you've got kilowatts, your volts, your amps, hertz. Okay. Notice the difference here. It's almost a divide by two, but this is the 480 volt system versus the 240 volt system. Depending on the wiring come out of it. Think of these generators like a backwards motor. Okay, it's almost the exact same thing. Instead of the motor spinning, you're spinning the motor. Okay, so all those principles of volts are gonna line up about the same. Okay, so this is where you're going to find it. Your RPMs, you want to nail in your RPMs, because now you have to match that with your motor. And you have to have a governor that's going to keep up with that and be reliable on it. Next thing you look at is you want to make sure you're dealing with the phasing properly. Remember, you're an electrician now, so you have to understand the phases. And in all of these power situations, you want to be developing power in 3 phases. You get an efficiency benefit on that. The math is the square root of 3 is the benefit of your power. So it's much cheaper than single phase power. And then the next one, this is the way some of the power factors are written. It's written the cosine of an angle. So this is cosine of 0.8. I don't understand why they do that. It's kind of a goofy number. You run through the cosine of 0.8 and the number is something like 0.99. So it's like a very small number. You know, it's basically saying this is almost unity power, but not exactly. There's a slight variation in that. But you want to pay attention to it.
Is that kind of standard with all generators?
No. More modern ones, yes. Some of the older ones just kind of followed the trend with the electric motors. Some of the older generators, you'd be generating, 0.9 power factor. You would have a problem at the genset. But now they've gotten them tightened up where they're almost at unity power. And then all you got to worry about then is your loads coming back to those affecting that power factor. And we'll talk about how you can address some of that too. Variable frequency drives are like magic on this system. And so that's another component that we'll look at to help correct for the power factor, the loading, etc. Okay, so here's an electric motor nameplate. You need to be familiar with these as well. So you're going to look here, horsepower, the volts, amps, and the service factor amps. Okay, so the service factor amps are in there basically because If you get bad power, this motor will tolerate that rise in amps up to so much. Okay? All motors are going to have these brandings on them. The other things you're going to look at is you're going to look at this service factor, that's how much you can overload it. The nominal NEMA efficiency of this particular motor, it's a big motor, so it's 95.8. I think Leon had showed it somewhere 90%. Any more, they're all more efficient than that. Okay, the bigger you get, the more the efficiency is. They all will have a listed power factor also, and this is a worst case scenario. I've yet to see a motor in the field that was as bad as what their power factor said. Again, remember, this is the regenerative power that's sitting back to mess up the waves of the amps and the volts. This is the particular motor that when it was loaded on that previous Genset was showing a power factor lagging of 93. So we'll look at motor controls, VFD and soft starters. These are pretty mandatory on a Genset, exactly for the point that was discussed previously, which is inrush current. When you start an electric motor across the line, it hits hard. Okay, so it's going to give everything it's got, and the amps spike almost infinitely. Think of that motor starting as a short. Okay, the hit is so hard on the service line because that motor's going from static to dynamic. When the electric hits it, it basically is hitting an across the line short on the motor. And then once it starts spinning, the current comes down and it starts to reach its equilibrium. Okay, so what you want to have these controls for is a drive so that you can ramp that start, but also so you can then dial in the speed of your motor by changing the frequency so that you don't overpump and subsequently so you don't overload the generator. That's the way to keep your power costs down, and it's substantial. It used to be these variable frequency drives weren't giving you a huge efficiency savings, they were just giving you a throttle control on your electric motor. It used to be that it would just burn off heat off the back. You'd have a big heat sink on them, and it was just burning off heat. But it gave you the ability to throttle your motor. Think of it like a rheostat on your stereo. Anymore, though, they use an integrated bus technology that converts the power in, basically breaks it, turns it to DC, breaks it back, and turns it to the loading. And what that allows it to do, it allows it to be very efficient in drawing the amps that's necessary to generate the work being done. They operate much cooler, but they give you great control over any electric motor. It's the way I would recommend doing this, with some caveats. The other is you should have a programmable soft starter at the minimum. The reason I say programmable is because you want to be able to control what your ramp into that full power is. Many soft starters, like a delayed start or a part-time starter or part-wind motors, the historical ways of soft starting, they're not going to give you the benefits that you would have right now on the Genset. Use something that can use some computer software. And there's so many of these on the market. These are just two that I've worked with. So here's the graph to discuss what we just talked about. Okay, we're talking about a motor. When it starts, this current, which is this axis here, basically goes to infinity, like you're shorting out a circuit. Once that motor starts winding, the current then comes down and it flows down to whatever its steady state current value is. Traditionally speaking, you need to design all of your electrical wiring, all of your starters, all of your line, so that they can compensate for this big spike of inrush current. Inrush current, the worst I've measured, is something in the range of 5 to 6x. Okay, it's a huge current. You've got a big old motor, when it hits hard, that current spikes huge, something like 1200 amps in some cases. I've watched it on an oscilloscope on across the line, one of those old one-arm bandit starters to see what it did, and I was just blown away. That really kills you even on your power bill if you're off the grid, because you're paying for that as your peak demand charge.
I got a question on
Yes.
that, because I've asked that question and I've always assumed that was factored in, but they all say, no, that's done over a 15 or 20 minute peak use period rather than that initial starting period. Which story is correct?
Well, I suspect it is, but if you look at this, here's where your start is, here's where your end is, and if you've got a start in the middle, it's
That's
contributing.
usually a very short interval.
Yes, but the magnitude is huge.
Yep, right.
So it may be just 2 to 3 seconds, but it's going to be a huge number, so it contributes.
So it will contribute, but not.
No, it's not like you're
Just
paying
base.
for this.
Yeah.
Instead of paying for this, you're going to be paying for this.
Okay.
When you're generating your own power and you've got a limited source, you want to avoid that. Okay, and this is what a VFD will allow you to do. Okay, you'll be able to ramp it up where you never really exceed that. Okay, there's tricks that you can do in the VFD because you're dealing with the frequencies where you can give it basically a signature of full voltage but lower amps, so you can spin it really fast to start it without loading. You think about your motors, you can do that on a well pump because you don't have to have all the horsepower of that motor until you've lifted the water from there all the way to the top of the column. Okay, so you can start spinning that pump pretty slow to get yourself ramped up on there without much grief. Okay, you think, oh, the water's way down there, it needs all the power at the start. It doesn't need all the power at the start. It just needs enough to spin it. If you go out to your vertical hollow shaft, you probably can take the cover off your motor and you probably can spin the nut by hand. Okay, that's how much power it needs to start until it gets a water column. It's actually flowing water. So keep that in mind. You can ramp up to that with control. There's a couple of caveats when you're talking about submersibles and drives, and these are very important. Modern submersible motors use thrust bearings that are water lubricated. Okay, so these are the friction surfaces on them. And by a thrust bearing, what it's doing is that bearing is basically riding on itself. But it has to have water between that, a film of water, to lubricate it, otherwise you'll burn out the motor in short order. So when you're starting on a drive, you can't start slowly, otherwise it's going to sit here and just ride on itself for a long time until it finally builds up sufficient speed to create that centrifugal force to throw those two surfaces apart to get a water film in there. So that's why you need to start a drive or a sub almost across the line. Right.
One thing to keep in mind on submersibles and VFDs is once you get over 400 foot from the drive, you've got to put a load reactor on. It will make the motor last way longer. We've gotten into situations where we're 600 feet, we're heating motors every 2 years. We put a load reactor on it, and that problem went away.
Where's your drive located? So is your
At the
drive
top.
located at the
Yes.
at the genset and your pump's a ways away?
It's at the pump.
Okay, so
But
you're running the power
bottom of the hole
to the-
is 600 feet.
Yeah.
So everything that we're doing now is anything over 400 feet has to have a load reactor on it.
Excellent. Thank you.
So by load reactor, you mean soft start or variable frequency drive?
It's on the motor side of the VFD. Otherwise, your spike gets too harsh in the sine wave. and
Okay.
It eats through the windings.
Very good. I did not
Yeah,
know that.
that's a simple way to explain it.
Oh, that's a great piece of information. Thank you. Okay, so there's a lot of specifics on these. This is literature from Franklin. When you get ready to be in this position, go ahead and study up on the requirements. They actually put a publication in all their motor manuals for their subs for the use of engine-driven generators. Now is probably a good time to say, going back to this, that this is about the point that you realize you need to be an expert on this, that you're not going to do all this yourself. This is a good thing to hire a lot of this out. Okay, there are people that are experts. You're getting to this is not something that, there's a lot of considerations to be had. Another point on these submersibles that's quite important is when you start to run them on a drive and you're slowing them down, it's good practice anyway to start looking at pump shrouds. Okay, is anybody familiar with pump shroud on the sub? Okay. It's almost mandatory in water above, say, 75 degrees here with Ogallala water where it's a lot cooler, you can get away from it. But as you start slowing the motor down, you want to size the shroud down that you're forcing water through to cool it. Heat becomes your biggest contributor on killing submersible motors. We'll step into electrical line sizing. This is the next part of it that's quite important. Again, when you're looking at the load size, you need to combine all of the electrical motors that are going to be down that system. Okay, so you can't just get it to one motor and then to the next motor, the next motor. You need to look at it. Do I have enough wire taking it for my entire system from here? These are just considerations we're going to make in sizing. Again, I'd recommend you visit with an expert on this. You can do your research to see if you're in the ballpark, but you really ought to work with the dealer on doing this, or whoever's providing you these products. Another consideration you have to have is the length of wire on the run, which includes all the extensions. The submersible drops is part of that as well. Remember that submersible, just getting power to the top of the ground is one thing. You've got to get power all the way down to the motor and the hole to make it really efficacious for you. You're looking at your wire material, which makes a difference. Your starter and motor controls going back to if you've got something that's going to be across the line, you're going to have bigger wire sizing to accommodate for that. And then the summary here is the installed cost of 4/0 direct burial aluminum is about $5.25 per foot trenched and installed. That's something you can budget towards. So this would be a typical system. This was the system actually that I had tested. This is the location of the genset. It's got a run going this way, and then a run and a run going this way. Okay, so you have to be mindful of that. This wire size just has to be enough to accommodate this. This wire size has to take care of this well and this well. This wire size only has to take care of this well. Okay, so that's kind of the map you're going to look at for your loading. Line loss calculations are important. This is again an actual one after the fact, but you can do this theoretically beforehand. What we did here is we took volts and amps at the submersible, and at the genset. And as you work through it, we come out to find that we had a loss of 2.7 kilowatts in the process. Okay, and when you go through the math, again, it's not much. It ended up being about a $250 cost per season, which to me is a number that says that this line was sized properly. Okay, if you went one size up, I don't think the economics of sizing up one size and get this down to say $5 per season, it would take a lot of years to accommodate that $200 savings, you know, with what your additional input cost is. But you want to run through these numbers. If you get this wrong, you've really only got one time to do it, or you're buying it again. And you're going to be better safe than sorry, size up rather than down. A couple of pictures to look at. Conduit is recommended on all of this. I know throughout the country here, there's a lot of direct burial line just put in. I have not seen direct burial line last very long. In my experience, the interaction with the coating, the aluminum in it, and the soil, it just degrades. So you're going to want to invest in a little bit of conduit. This is a nice, this smooth wall HDPE. You can have your wire sink in that, and so you just drop it in the hole as you go. That's what I recommend doing. So some operational procedures that are worth considering. And we'll step through a couple of these. Our last two slides to finish up on is a summary. You want to start this genset motor without a load, and where possible, allow it to throttle up before you start putting loads on it. Okay, the commercial generators that will come out, they have a green button you start, and then you can't do anything with that until it reaches the operating conditions that the manufacturer specs. Okay, you're not always going to be able to do that on your well because if, you know, for example, this is one of the reasons why you might want a radiator rather than cooling coils, is you go out there, you can start it, warm it up with a radiator, you don't have to worry about pumping water yet. Or if you've got cooling coils, you better start getting water to the top really quick, just like you would have to with a natural gas scenario. Okay. The next step is to engage the generator breaker to energize the electrical system. So you got power from the generator, now you're going to engage the electrical system. Then you're going to start loads one at a time. This is to help minimize that accumulation of inrush current. Okay, so you're going to load it, allow the motor to recover. Load it, allow the motor to recover, load it, allow the motor to recover until you reach your full loading. Think of it like driving your truck. If you're loaded and you just give it full throttle, it's hard to get moving. Okay, the transmission absorbs a lot of that. You don't have a transmission in this case. So you want to load it, allow the governor and the motor to compensate for that. It is a functional practice where possible to put multiple starters near the genset if they're close enough. If they're a ways off, you don't want to do that. Your shutdown process is just the backwards of that. You remove the loads one at a time, disengage the main breaker, idle the motor back for a short period to allow it to cool down. Remember, if you've been running it for a month steady, you're going to want to let those differences in metals cool back down so you can reach a comfortable state and shut it off. Then your maintenance schedule, to reiterate, your oil changes monthly, air cleaner as needed. And my recommendation is because of the startup procedure, to don't shut it down frequently if you can help it. Okay, so it's not something you're just going to turn on and off every day. Now I know in this scenario our operating systems are not really like that, but keep in mind when you turn it on, you may want that thing running for the whole month while you're irrigating. You take the loads on and off as you go, but that may help you understand or prioritize where you place that genset. You may want the pump right next to the genset to be your priority one, the one that's going to be running all the time, and then your satellite ones to be the variable. Okay, so some more considerations. Just like that, locate the system genset at the largest well, pump on the system. Mostly so that you can get the most water up in the shortest amount of time. You've got the shortest run of cable to your heaviest load, and it's your primary operating well, so typically the one's going to produce the most water. And then if you're going to automate VFDs, you want to be careful to only have one automated VFD on at a time. Okay, they can start to fight each other if you're not careful. If you automate them downhole and they're isolated, that's one thing, but if you automate them based on a pivot pressure or a line pressure, those VFDs will dance with each other and you'll never get it to line in. Okay, so if you've got multiple wells, make that consideration. I would recommend a VFD as part of the complete system of the genset. It is very helpful. These are things that we've already stated. The last thing that's kind of a trick that I think is useful, I've installed quite a few of these, is automatic solenoid oilers at satellite wells. If you've got not a submersible but a vertical hollow shaft that you have to oil, something that's got duplicity where you've got an automatic dripper as well as a manual dripper, you keep that manual dripper where it's on once every 30 seconds drip, and then as soon as it powers up, you can start the one that's set to where you want to run at. That's really useful. It's going to be one guy running around from site to site. That way you can actually turn them on, and then you can make your lap around and check your operations without having to do that in reverse. Okay. Steve, you going to shut us down, or we got time for a little more questions?
Questions.
Okay. Any thoughts, any things that weren't answered, some questions?
In your opinion, how critical is having the hertz right? Because I've been in different arguments. Some guys are not concerned, and the next guy is if it's not dead at 60, it's
Yeah.
going to burn the motors up. What do you think?
Well, most of these motors can tolerate a variation in hertz. That's what a variable frequency drive is doing. But if you were generating, I would do everything I can to make sure that's at 60 hertz. That way you're starting off with the best nameplate rating for anyone. Some of the older motors may not be very good at compensating for hertz. Usually on the drive, what you want, or the motors that they have, include much larger housings to dissipate heat and much larger components that they can take the torque loading of a smaller or slower RPM, where a smaller motor may not be able to do that. But really you ought to be at 60 hertz if you're generating it yourself.
I had I think they're just power correction capacitors on the back of the panel that North Plains made us put on. We switched over and then we put a soft start on it, and the electrician just basically disconnected that capacitors. Are those going to help me if they're hooked up, or does it matter, or is there enough difference there that?
So if you're on grid power,
Mhm.
it may not help you a whole lot.
It's just to help
It's to help the system.
the system.
But it could help you in some way. If it's way off and you correct it back a little bit, that certainly can help you. I mean, if it's coming in at 80 and you correct it to 90 on your end, it'll help a bunch, but it's certainly going to help the grid more so.
It's more for the grid is what they're doing. But it won't hurt to hook them back up.
No, it certainly would be nothing negative to have them hooked up. Yeah, unless you're going backwards. You can do that too. Yeah, because you're manipulating it, so you can drive it the wrong direction if you're not careful.
Okay.
That electrician will know about that. Thank you all.